Hello everyone, so today we're going to talk about Chapter 5.3, the Fundamental Theorem of Calculus, which is proudly supported by Brad Pitt and the University of Pittsburgh. I hope you get the pun. The relationship between the net area and the graph of the antiderivative. So basically, when you graph the net area of a graph, you're graphing the antiderivative. So here we have the function g of x from the interval 0 to x of f of t dt. So when we find it, so what we're doing is finding the area from each point. So f of 0 from the interval 0 to 0 f of t dt equals 0, so because there's no area when there's no change in points. G of 1 from the interval of 0 to 1 f of t dt is 1/2. G of 2 from the interval of g of 1 plus the interval of 1 to 2 of f of t dt is 0, because both are positive 1/2 and negative 1/2, so the net area of that would be 0. And then g of 3 is there, g of 2 plus the interval from 2 to 3 of f of t dt, which becomes negative 1/2. Then g of 4 is g of 3 plus the integral from 3 to 4 of f of t dt, which equals 0. And then g of 5 equals g of 4 plus the integral of 4 to 5 of f of t dt, which equals 1/2. And then g of 6 equals g of 5 plus the integral from 5 to 6 of f of t dt, which equals 4. So when we estimate g of 7, we do g of 6 plus the integral from 6 to 7 of f of t dt, and we get 6.25. Where does g have a maximum value and where does it have a minimum value? So the maximum value occurs at x equals 7 because g of 7 is at its greatest, which is 6.25. And a minimum value occurs at x equals 3 because g of 3 is negative 0.5, which is the lowest. So when we plug in all of the points of the area that we got above, we get a rough sketch of the graph of g of x, which is the antiderivative. So here's the official fundamental theorem of calculus part 1, or the FTC1. So if f is continuous on the integral of a to b, then the function g is defined by g of x equals the integral from a to x f of t dt on a is less than or equal to x, which is less than or equal to b. It is continuous on a to b and differentiable on a to b, and g of x equals f of x. So in words, the derivative of a definite integral is its upper limit x is the integral evaluated at the upper limit of x. So here's an example using the fundamental theorem of calculus part 1 to find the derivative of a function, because that's what this part does. So in this example, we'll use FTC1 to find the derivative g prime of x of the function g of x from the integral of x to 0 tangent v dv. So we'll use the integral from b to a of f of t dt equals the negative interval from a to b of f of t dt, and when we do that, we get g of x equals negative 10x. So here's the fundamental theorem of calculus part 2, or FTC2. So in this theorem, if f is continuous on the interval of a to b, then the interval of a to b of f of x dx equals f of b minus f of a, where f is any antiderivative of f that is a function such that f prime equals f. So as we can see with this, if you write it out, the constant cancels out in a general antiderivative, hence why we don't need it when we calculate the evaluation of the integral. So in words, if we know the antiderivative f of f, then we plug in the endpoints a and b and subtract, and as I stated before, the arbitrary constant would cancel out. So in this example, we'll use part 2 of the fundamental theorem of calculus to evaluate the integral. So the integral is from 0 to 1 of x squared dx, so that will equal f of 1 minus f of 0. So first we'll find the antiderivative, which is x cubed over 3. If we remember our rule, x to the n plus 1 power over n plus 1. That's how we got that. And then we'll evaluate it from x equals 0 to 1. So then we simply just plug in the endpoints and we get 1 to the third over 3 minus 0 to the third over 3. And that quite simply simplifies to 1/3 minus 0. Therefore, the integral from 0 to 1 of x squared dx equals 1/3. Thanks for watching.